This is, as I said, the third week of our three-part series called Atoms, Quarks, and Strings, The Origins of Matter. And in the first week, I talked about from atoms to quarks. And in the second week, Cyrus told you all about the Standard Model and the fundamental forces and the origins of mass. And this week, the two of us are going to try to tell you about things beyond the Standard Model. So, whereas everything up till now has been absolutely fundamental and clear, and simple, now we're going to get speculative. No, the truth is, up till now, everything has been things that we've measured at experiments, and now we're going to start talking about the things we would like to be able to measure at experiments over the next weeks, months, years, decades, and talking to some of my colleagues, millennia. So, I'm going to start by talking about why do we need anything beyond the Standard Model? Isn't it perfectly good as it is? Then Cyrus, after the question and answer period, Cyrus is going to step in and tell you about how strings in quantum mechanics give us gravity and other stuff. And then I'll finish up by talking about extra dimensions that you could possibly see. So, in the spirit of David Letterman, of late night television, the top 10 reasons we need physics beyond the Standard Model. Reason number 1. There are 58 fundamental particles plus their antiparticles in the Standard Model. So you may remember from week 1, we started off with this beautiful periodic table of the elements that Mendeleev showed us, which gave us a view in the 1800s of the fundamental particles of nature, namely the atoms. And then soon enough, we discovered that there were a few more, 4,100 in fact. And we decided that it was a terrible, terrible mess. And we couldn't possibly live with 4,100 fundamental different nuclei. Okay? And things got a lot better pretty quickly, so that by 1932, if you had looked at what are the fundamental particles of nature, it was the proton and neutron and electron, and all the physicists had big smiley faces on, because that's beautiful and simple. 3 is a wonderful number. We like small numbers. Okay? We like numbers like 0, 1, 2, 3, 4, 5. But we don't like when our lists of fundamental particles look like this. Okay? And this is what, and I had meant, in fact, to bring in a book about this thick that describes each of these particles. It's called the Particle Data Book. And so as that book got thicker and thicker, people became less and less happy about the state of the fundamental particles. And it was Gell-Mann and his collaborators that said, oh, actually, things aren't quite so bad. Really, there are only a few fundamental particles. Here they are, the electron and its neutrino. We soon learned about the muon. We had learned about the muon and its neutrino. But the proton and the neutron and all those particles that were in those huge tables, they're all made just of up quarks and down quarks and strange quarks. And isn't that nice? We're happy again. Well, time has gone on since then. We've learned that there are more leptons, light particles like the electron and its neutrino. There's the tau particle and its neutrino. We've learned that there aren't just up type and down type and strange types of quarks, but 3 more quarks, the charm, the bottom, and the top type quark. We've learned that each of those fermions, and these are, remember, called fermions, except maybe the neutrinos, come in both a left-handed and a right-handed variety. We've learned that each of those quarks come in 3 different colors. And so our list of fundamental particles now looks something more like this, with 9 different leptons, and I can't remember how many different quarks. You can multiply 9 times 4 is 36. And then we added the fundamental force carriers, the photon, the carrier of electromagnetism, the W plus, W minus, and Z particles, which carry the weak force, and 8 gluons, which carry the color force. And then there's this one particle that we think we're about to discover called the Higgs particle, and that's 58. So that's not so good. We're back to a situation where we're kind of worried that we have too many fundamental particles once again. It isn't quite as bad as 58. if we actually put these particles together into things called representations, which you should stop by your local mathematician. We have a couple of them there in the middle, and they can tell you all about what representations are. But we can really organize this into nice small sets and are left with just 19 representations of fundamental particles plus their antiparticles. So that's reason number one, why we might want some physics beyond the standard model. What is reason number two? Well, our standard model of particle physics contains 3 forces, and there are 4 forces. We're missing one. What forces does it contain? Well, I showed you the photon that carries the electromagnetic force. Okay. I showed you the 8 gluons. We talked about those last week. Those carry the strong force, the force that holds together the quarks and binds them into protons and neutrons and pions, all the baryons and mesons. And then these 3 others, the W plus, the W minus, and Z, that are the carriers of something called the weak force. What about gravity? Well, the standard model has nothing to say about gravity. It's not contained in the standard model. So reason number 2 why we need physics beyond the standard model, there's no gravity in the standard model. So remember I told you that we really like small numbers, 0, 1, 2. We don't like really big numbers. Well, I say we need like small numbers. We like numbers that are around 1 or are exactly 0. So 2 is a good number, 3 is a good number, 0 is okay, but 75 and 100,000 and 10 to the 60, those are not good numbers. And it turns out that especially when we try to add gravity, we find that there is a small number or a big number. So there's a number, a mass, that characterizes gravity. Okay? We can form this number just out of a combination of 3 fundamental constants of nature. One is this thing called h bar. H bar tells us how important quantum mechanics is in nature. The bigger h bar is, the more important quantum mechanics is, the stronger quantum mechanical effects are. Okay? It's called Planck's constant. Okay? There's c, which is the speed of light, and there's g, which is Newton's gravitational constant that tells us how strong the force of gravity is. And if we just put those together, we can form a mass. And that mass is the mass at which we expect that quantum mechanics will become important for gravity. How big is that? Well, it's about 10 to the 19th. That's 10 billion times the mass of the proton. Okay? We have not been able to take any fundamental object like a proton and give it this much energy, m Planck. Okay? But one day, maybe, we will find a situation where we could in fact find particles that have energies of m Planck, 10 to the 19th times the mass energy of a proton. There's another fundamental scale, and this one is in the standard model. That is the mass of the W. Okay? That is a fundamental scale of the standard model, the mass of the W or the mass of the Z. They're all kind of around the same thing. It's actually something called the weak scale, and that is about 300 times the mass of the proton. So here we have 2 numbers. One number that characterizes how strong the gravitational force is. That's this thing, the Planck mass, 10 to the 19, 10 billion times the mass of the proton. And this other number that characterizes how strong the weak force is. Okay? And that's 300 times the mass of the proton. And the ratio of those is about 4 with 16 zeros after it. Or in other words, 40 million billion. Okay? So that is a very, very large number, and we don't like to have such large numbers in our theories. Okay? That's a philosophical problem. Some would say also a technical problem. But we would like to solve what's called this weak hierarchy problem. We'd like a model that explains to us why is gravity so weak, or why are the other forces so strong compared to each other. Okay, so that's problem number 3. Oh, I should point out that we can also think of the Planck, instead of the Planck mass, we can talk about the Planck length. This is the length scale at which we expect to see the quantum mechanical effects of gravity, and it's about 10 to the minus 35 meters. We're very far from being able to explore that length scale at our accelerators, with microscopes, with anything else like that. So far, 3 of the top 10 reasons why we need physics beyond the standard model. Too many particles, no gravity, and a weak hierarchy problem. And finally, we may have too many particles, but we also don't have enough particles. We're missing the missing matter. What is the missing matter? Well, when we go out and look at large objects, really large objects, like galaxies. So here's a picture of a galaxy just very much like our own. It's called NGC 7331, which is a very catchy name. And it, as it kind of suggests, just looking at it, you'd kind of think, well, this galaxy is spinning. Okay, it's spinning, but how fast is it spinning? And the amazing thing is that we can measure how fast it's spinning. We look at the stars and with the light coming from this galaxy, and things that are moving towards us will appear bluer than they would if they weren't moving, and things that are moving away from us will appear redder than they were if they weren't moving. This is called the Doppler effect. If you've heard of Doppler radar on the weather, that's basically the same thing. So when things move towards you, they appear redder. When things move away from you, towards you, they appear bluer. Away from you, they appear redder. And so we can look at the light from the galaxy, and we notice that this object is spinning because on one side everything is moving towards us, and the other side everything is moving away from us, and we can actually measure how fast the galaxy is spinning. Well, what would we expect? We would expect, in terms of how fast it's spinning, well, we would expect that inside the region of the galaxy, exactly how fast it's spinning would be kind of complicated, because it would depend exactly how much mass there is inside the galaxy. As we go out, there's more mass between us and the center of the galaxy, and the amount of mass is rising. On the other hand, we're getting farther from the center of the galaxy. It's not clear whether we should have to go around the galaxy faster or slower as we move out. But eventually, when we get way out here to the edge of the galaxy, there doesn't appear to be any more mass further out. So when we reach the limit of the galaxy, that's all the mass there is. We see everything, all the stars, all the gas, all the dust. And at that point, the speed at which any little thing that we can see out there is moving should start to be slower and slower. Because it should take, if you were going too fast, you should just fly away from the galaxy. Okay? So what we expect to see is that as you go out in radius, first of all, the speed at which you're going is increasing. And here is, I've put the galaxy down here to show the extent of the galaxy. So in the first bit, as we go out in the galaxy, something complicated happens where the speeds go up and then they go down. But eventually, as we get further out, the speed at which you're going around the center of the galaxy should go down and down and down, like in this curve A. But when we measure it, instead we find that the speeds are the same as we go out, like this curve B. So what does this tell us? It tells us either we don't understand the force of gravity, that Newton's law is actually wrong when we get far out there, or general relativity is wrong, or there's actually extra stuff out here that we just can't see. And that's what we think is going on. We call that missing matter or dark matter. And we could ask, well, what could that dark matter be? What might we not see that could be there in the outskirts of galaxies? Well, maybe it's black holes. Stars that have collapsed to such a density that even light can't escape. That happens to stars at the end of their lives. Or maybe it's neutron stars, which are also failed stars that didn't manage to collapse quite as dense. Imagine taking the sun and collapsing it to about 6 or 7 miles in radius, about 12 miles across. That's pretty small for the sun, which is about 1 million miles across. But so it's pretty dense, but it's not dense enough to be a black hole. Or it could be stars that fail to ever ignite. Things kind of like Jupiter, but a little bit bigger. Or maybe it's planets. All of these things would appear, you'd think, pretty dark. And as they don't glow very well. Okay? They also don't absorb light very well. Or really cold gas, or really cold dust. Ordinary stuff, neutrons maybe. Or neutrinos, these particles that we've mentioned. Well, it turns out that none of these things can be the dark matter. We can go one by one through each of these, and over the course of the last 20 or 30 years, people have considered each of them. They've said, oh, what does it take to make a neutron star, and what do we have seen, and what would it look like? It turns out it would leave too much junk out there. When you make a neutron star, it's very inefficient. You throw out a lot of junk. What about things like Jupiter? Well, Jupiter actually shines in the infrared. So none of these things are good dark matter. In fact, none of the objects in the Standard Model are good dark matter. So I told you I would tell you 10 reasons. I'm not going to tell you 10 reasons. I'm just going to tell you 4. So here are the top 4 reasons why we need physics beyond the Standard Model. Too many representations of fundamental particles, no gravity, a big number called the weak hierarchy problem, and there's no dark matter, which suggests that maybe there's new physics that we have to look for, new particles, new forces.
I don't get matter.
You don't get matter.
Well, the reason I say that is in my extremely limited understanding, matter has substance, meaning, I can touch it, or it could be matter, but it's very dispersed like the air.
Right.
But dark matter, how come we never bump into it?
We have examples of matter that we know that you don't bump into. So right now, there are billions of neutrinos passing through you. We know that because we can manage to make measurements. They come from the center of the sun, which produces the sun produces lots and lots of neutrinos. Those neutrinos flow freely out of the sun and then travel through the interplanetary space, and they are passing through you right now. They go through the building without any problem. In fact, they would go through about a light year of lead. Okay? But we can build detectors, and there are so many passing through that detector that occasionally one of them will light up the detector. So we know that there are particles of matter that, even though they're there, we aren't very good at seeing them. We believe dark matter is, so the standard model of dark matter is some other particle that we don't know what it is. We have some ideas of what it might be. They go by names of things like WIMPs or axions that also would be flying through all of us right now, billions of them, or millions, depending on how heavy the particle is. And we are looking for them at the bottoms of mines in South Dakota and Minnesota and Sudbury, Ontario, and under the Alps, and the Chinese are building a lab. So yeah, some types of matter just aren't very good at interacting with other types of matter, like the type that we're made of, neutrons and protons and electrons.
In terms of energy units, 10 to the 19 times the mass of a proton looks like a lot. But in terms of familiar weights, that's only, what, 1/10 of a milligram or so. It seems that if you're going to worry about gravity becoming important at that scale, it ought to be detectable because things that go, in the tenths, hundredths, thousandths of a milligram are actually commonplace in science.
Right. So this is a very good question. Why am I worried about things like that are about this Planck mass, which is only actually a small fraction of a gram? After all, I have a pencil here that weighs a lot more than a Planck mass. But the thing is, what I really should say is, what I need to do to find to put myself in a situation where I expect the quantum mechanical effects of gravity is take that, small fraction of the gram and compress it into a space about a Planck length across. So 10 to the minus 35 meters. So that's pretty hard to do. It's not hard to find a Planck mass worth of material. It's actually very easy, but it's really hard to find it anywhere in the known universe compressed to within a Planck length. In fact, we don't think that's happened in a very, very, very long time, since a tiny fraction of a second after the beginning of the universe.
Welcome to Act 2. Strings plus quantum mechanics equals gravity plus stuff. So I want to start off with a couple of disclaimers. The history of string theory, I believe sociologists will study centuries from now to understand the dynamics of science. It's been long and windy and really interesting, and in 15 minutes I can't go through any of it. Second thing is it's a theory in which to actually delve into it in detail is intensely mathematical. And the mathematics is both arcane and beguiling when it exists. One of the real things that I hope you come away with is that string theory is actually a fertile source for invention of new mathematics, and probably will be for quite some time to come. One corollary to this, last week, of course, I punctuated the discussions of the various detectors and accelerators and particles with, highlighting people, particularly from Case Western Reserve, that had won Nobel Prizes along the way, including for the discovery of neutrinos. There are no Nobel Prizes that have come out of string theory. And I don't actually expect there are likely to be any in my lifetime. There has been a Fields Medal. The Fields Medal being, in some sense, sort of the analog of a Nobel Prize for mathematicians. It's awarded once every 4 years, and only to mathematicians under the age of 40. It's been said that really the physics and mathematics of string theory is a bit of 21st century, maybe even 22nd century mathematics that got dropped into the late 20th century. And that was said by Ed Witten, who was probably the greatest mathematical physicist of certainly the last 50 years, who in fact won the Fields Medal for work that was inspired by him, or by trying to understand string theory. But what he really did was figure out an intrinsically three-dimensional way of characterizing knots, which had been a very famous unsolved problem for a very, very long period of time. Now, last week I managed to go through without showing any equations. I'm going to show one this time just to give you something of the flavor of the strange land in which we live in. So we're thinking about, used to summing series. 1 plus 2 is 3, 1 plus 2 plus 3 is 6, and so on. 1 plus 2 plus 3 plus 4 is 10. So if you keep on going to infinity, the usual way of thinking about this is that this is a divergent series that is not well defined. However, at least going back to really, really interesting Indian mathematician of the early 20th century, Ramanujan, developed a technique for thinking about divergent series where you relax some of the conditions that you usually apply to what you mean by addition. But the result is that that sequence 1 plus 2 plus 3 on to infinity actually has a well-defined and finite answer, and it has the paradoxical result that the sum of positive integers is neither positive nor an integer. It's minus 1/12. Now, to actually go through and give you a detailed understanding as to why this makes sense and why you shouldn't just lock me up requires more than 15 minutes. Now, in preparing this talk, last week, I had the virtue of I could show you wonderful pictures of detectors and accelerators and event displays and so on. We don't have anything like that to show for strings, and so I decided to opt for sort of a retro approach to it. I actually did a dry run of this lecture at the chalkboard. And the easiest way of creating the illustrations was actually just to give the lecture, and Patricia Princehouse kindly photographed me along the way, and we've converted it into a PowerPoint. So it's sort of a high-tech way of a low-tech lecture. So up until now in this course, we've been talking about particles. And so point objects that have a position in space and time and move along. So what I've illustrated here is we've got x in one direction, time in another direction, like we had last week. And we've got a point particle moving through space-time, and the line just shows the trajectory that it's been following along. Now, in everything we want to do today, we want to say, okay, particles have given us a really, really rich theory. It's the most accurate theory ever devised by man. It's what I talked about last week. We can calculate things to 1 part in 10 billion. We can measure them to 1 part in 10 billion, and they match. However, it's got the flaws that Glenn laid out before. So this is ahistorical, but you remember last time we had sort of a model of quarks attached to the ends of a string as a model of mesons. So let's think about if the fundamental objects actually were little bits of string. And what you see here is a drawing of a little bit of string sitting there in space-time. And as it moves along, it traces out a sheet. And so what you see there is sort of the world sheet of the string as it moves through space-time. Now, that was an open string. Right, it's got 2 ends to it. We're also going to be interested in closed strings, little loops like this. And so as the loop moves through space-time, it traces out a trajectory as well that looks like a cylinder. And so just to compare, open string moving through space-time on the left, closed string on the right. The one looks like a sheet, and the other one looks like a sort of a cylinder moving through space-time. Now, point particles were, in some sense, kind of boring, right? They can move through space-time, but they don't really do much of anything other than that. I mean, they can bump into other particles. But strings are different, right? One little bit of string can talk to another bit of string, and they can interact. And so you understand this quite well. Take as model strings that you know, like a stringed instrument, a string on a violin or a guitar. And let's look at, imagine looking at just one of them and plucking it. And as you pluck the string, right, it vibrates. That's very fast. So if we slow it down for purposes of this illustration, the string vibrates up and down and up and down. Now, unplucked, it's just straight and goes across there. So we can think about categorizing this. You know that in addition to a violin string, in addition to the fundamental frequency, you can also excite harmonics. And so you've got it unplucked, plucked in the fundamental frequency. The first harmonic, where you hear the overtone at twice the frequency of the fundamental. You can have a higher excitation, a third order, and so on and so forth. And in fact, you can have an infinite number of these. Now, when we turn on quantum mechanics, basically take this model of a vibrating string and apply the machinery of quantum mechanics to it, what happens is that each of those vibrational levels, each of those harmonics becomes a particle with a different mass. And so the first thing we see as a result of this physical picture that the fundamental objects are not particles but are strings, is that it tells us that it really implies the existence of an infinite tower of particles of steadily greater mass. In fact, integer multiples, the mass squared goes like integer multiples of a fundamental. Now, one of the things we learned last week is that particularly important are the carriers of forces, the gauge bosons. And if you recall, the photon, for example, is a massless gauge boson. The mass is 0. So one of the first questions is can you get this out of the theory? Right? Because if you can't, then it's not going to be a very good candidate for explaining the world. And the answer is you can. The first excited state of an open string has mass 0, but only in 26 dimensions. So remember, we live in a world in which we have 3 spatial dimensions and 1 time dimension, so a 4-dimensional space-time. So this is only a candidate for the kind of things that we saw last week if in some sense the world is really 25 spatial dimensions and 1 time dimension, which is a lot more than we're aware of. So that would seem to be a flaw. It also has another problem. Namely, the when you go through that, the lowest state, the unplucked string, actually turns out to be, if you go through it, a particle moving faster than the speed of light, and that's a real no-no, as we alluded to briefly. And the final part is you remember we had the quarks and leptons, which were called fermions, and there's no such objects in that theory. So how do you add those in? Well, you actually add more dimensions, but these are funny dimensions. You're used to a space, we're used to a space in which we've got an x direction and a y direction. If I measure the x position of a particle and then the y position of it, and then do it in the other way around, those two are, and multiply them together, xy is equal to yx. The trick here is to add in extra dimensions say called theta 1 and theta 2, where theta 1 times theta 2 is minus theta 2 times theta 1. And again, a semester or two would give you the technical prowess to be able to deal with that. At the moment, just treat this as we're adding in extra dimensions that are unlike anything you've ever encountered before. Now, the other thing is to make this work, you have to build in another feature. You remember last week with the Mexican hat, right? We rotated the Mexican hat, and it looked the same. There was a symmetry there. So in this case, we're imposing a symmetry as well it corresponds to a rotation between the dimensions we know and these new dimensions. And that rotation is called a supersymmetry. You turn the machinery of quantum mechanics, and what comes out is this theory only works in 10 dimensions. So that's a little better than 26. Albeit at the cost of some dimensions of a sort we haven't encountered before. It has the massless gauge bosons in it. It has massless fermions, that is, candidates for all the quarks and leptons that we encountered last time. And there's no tachyon, so this is all very, very good. Now, mind you, there's still an infinite number of additional particles. Remember, Glenn was upset because there were 58. And now we've got an infinity of extra ones. So last week, we explored how particles interact, right? The pictures I showed were where you saw before your eyes electrons colliding with positrons, creating gauge bosons, and then creating other particles. And we drew Feynman diagrams, and generically, particle collides with particle to make new particle. So the picture here with strings is to try and do the same thing. You imagine an open string coming in, another open string coming in, and making another open string going out. Now, you can really think of this as sort of like a rubber sheet that you can stretch as much as you like. And the point is there is no point interaction. This is all kind of smooth there. And here I am just emphasizing that you can think about stretching these. Now, at the end of last time, one of the diagrams we looked at that was key for the production of the Higgs boson turned on loops of particles. Well, you can make loops of strings, too. This is a loop with 1, 2, 3, 4 open strings, 2 open strings colliding to make 2 open strings. But different from what we had before is the loops now have insides and outsides. And these 4 particles are all coming off the outside, but you could imagine having 2 of them come off the inside, which is what I've tried to sketch here with. So we've got 2 particles on either side coming in with a loop, and then off the inside, we're taking 2 particles out like that. Now imagine pulling these apart and stretching it. And you get something that looks like this, like a cylinder. And in fact, what you see is that this, as you stretch this loop of open strings, there's really a closed string hidden in between it, so that automatically the theory of open strings includes closed strings. Remember? We quantize the closed string, apply the machinery, and go to it. Same sort of power, the tower that we had before. And the lowest one is, in 10 dimensions, is massless again. And so the question is, what is it? So we can look at its interactions. And you can collide an open string with an open string to make a new open string by sort of the seat of the pants diagram, right? So think of the waist as being the one that's created and the cuffs going in. You calculate very, very hard, right? Very, very hard as to what this actually implies. And what you discover is that this is actually a theory of general relativity. The massless particle is the graviton, the quantum of gravity. The interactions are exactly those of Einstein's theory of general relativity. And plus there's corrections that become important at about 10 to the minus 35 meters that we wouldn't see. So what's beguiling is Glenn said the standard model is problematic because we didn't know how to put gravity into it. Here we've got a situation where we start off with something that is just little bits of string, and gravity comes out automatically. So the good news is we've got gauge bosons, gravity, and fermions. The prospect of uniting gravity with everything else is beguiling. The bad news is we're stuck in 10 dimensions, and well, from my perspective, supersymmetry is bad. We haven't seen it at the LHC. So how might this have something to do with the real world? The idea is suppose this is one of the extra dimensions, but rather than being flat, it's rolled up, right? It's curled up small. And so if you're an ant, crawling on the surface, it looks two-dimensional. But if it's curled up really, really small, and you're much bigger than it, this just looks like a line, right? The extra dimension disappears altogether. You don't see it at scales large compared to that. So the idea was to curl up the extra dimensions, extra 6 dimensions. If you want certain nice low energy properties, there's a number of requirements on how you can do that. Candidates for that are called Calabi Yau Manifolds. This is a picture of a 3-dimensional cross-section of a typical Calabi Yau manifold, so a little complicated. It was thought there were about 100,000 of them when this was first proposed, and the idea was you just go through the 100,000 and one of them will be the real world. Doesn't work that way. There's many, many more of them than that, and it gets more complicated. Just very briefly. We had strings that had free ends. The idea was, if you nailed them down, you'd break all the nice symmetries. But if you were in the extra dimensions, you don't care if they're nailed down. And so in the 1990s, it was realized you could have your string end on a membrane. A 2-dimensional sheet in the extra dimensions that strings just end on. Or you could have a 3-dimensional analog of a brain, a 3-brain, or a 4-brain, or a 5-brain, or a 6-brain, or a 7-brain, or even a 10-brain. So the string theory that I described up until now is an infinitesimally small part of what we now understand the full theory to be. So the task of figuring out what's the actual ground state of the theory, where our world lives in this unimaginably large space, is beginning to look a little daunting. My freshman orientation at MIT, at the end, after the president's talk, a banner rolled down to this effect, and I sort of feel like it applies to sort of the program that had been set out for string theory. So where do we go from here? String theory is beguiling. It's vast. And as we continue to explore it, because there's no doubt it's sufficiently seductive that many people will continue to devote their lives to it, we're going to construct an awful lot of new and probably quite surprising mathematics. And we're also going to realize as we do that many of the things we think we know about the real world are in fact based on prejudices that might not be true. And in the final section, Glenn's going to pick up on that theme and talk about just one example of that.
It was noted that at one time you were deeply involved in string theory. What caused you to move on? Yeah,
I started working on string theory in 1983. In 1983, I think there were about 50 papers on it. 1984, there was a major breakthrough related to parity, which Glenn talked about in the first one, showing that you could actually have parity violation. So by 1987, vast numbers of theorists started working on it. There were, I think, about 8,000 papers published on it in 1987 to give you an idea of the level of activity. That's continued probably order of a few thousand papers a year on average since then. I thought when I started working on it, it'd take about 25 years to make contact with the real world. By 1990, I just realized I was giving more talks in math departments than physics departments, and that really, in order to tackle the problems, that there was an awful lot of mathematics that needed to be invented. And so I decided it was unlikely to happen in my lifetime. So that's when I went off and did the stuff that I talked about last week. I've come back and worked on it from time to time since then, because it is very beguiling and very seductive. And every time after about a year, I've decided I was right in 1990 and gone back to things more grounded in things that we can actually see and do in my lifetime.
Picking up on that last question, you mentioned earlier that there have not been any Nobel Prizes awarded. Is this because there isn't the impetus to continue the research, or that it hasn't been recognized?
Well, no, it's neither. You win a Nobel Prize on the theory side for predicting something that someone can then go out and measure. It's sort of, Einstein, when he did general relativity, predicted that the sun would bend starlight. Immediately after World War I, there was an eclipse, and there was an expedition out, and starlight was indeed seen to be bent around the sun. And it was like a prophet who had made this prophecy, and then it was confirmed. And that's sort of what Nobel Prizes for theorists are. You make a prediction, and it turns out to be right, testable in great detail. String theory hasn't made any predictions yet. It's beautiful qualitatively. It's very seductive. But it's not the real world. We don't know where it may well be the right theory. I think it's probably the most likely framework for something that would be the next stage of the theory. But we don't know where in this space the real world lives, and so there's no predictions. And absent predictions, there's no prizes in Stockholm.
Where does what math do you need that you can't use for the string theory?
Oh, you mean what math does not exist yet?
Yes.
There's whole categories of it. Let me see if I can give some quick examples. So a simple example is the Calabi Yau manifolds that I talked about. It is, you know what the properties are for something to correspond to it. You want to know, in some sense, how many of them are there? That's not a question that is answered at this point. More generally, I think there's issues of the space in which this lives in is really, really big, and we don't know what the representations are.
Okay, so we've learned about strings and quantum mechanics equaling gravity, and we've learned that in order for string theory to work, we need extra dimensions. And we just learned that those extra dimensions are really, really hard to see. Why? Because they're wrapped up so tiny. How tiny? About a Planck length. In other words, to travel around one of those extra dimensions, you have to go maybe 10 to the minus 35 meters. If the extra dimensions are that small, we will not see them, which is why no one has been doing experimental string theory. Okay? But I'm going to tell you about a possibility that actually those extra dimensions are larger. And this would be very exciting because it would allow us ultimately to do experimental string theory. So we start at that weak hierarchy problem, which before 1996 we viewed as the question of why was that mass that I told you, M weak, which characterized the scale of ordinary interactions, electromagnetism, the weak interaction. It told us how strong those interactions were. Okay. Why is it so much smaller than the scale which characterizes gravity, called the Planck scale? Another reason way to ask that is, why are the non-gravitational forces so strong? And you might be saying, what do you mean the non-gravitational forces are so strong? Isn't gravity really strong? After all, if I drop this, it will fall. Gravity is strong. But I want you to realize that looking at me holding this, that I am defeating the entire Earth. The entire Earth is pulling on this remote and I'm defeating it with electromagnetism. So gravity is so weak that me standing here with a mass that is, a fraction of a billionth of the mass of the Earth can defeat the Earth with electromagnetism. So electromagnetism is incredibly strong compared to gravity. Now, so up until 1996, the question we asked is, why are these other forces, electromagnetism, the weak force, which is weak but incredibly strong compared to gravity, and the strong force so strong? And the great insight of 1996 was to turn the question around and ask, why is gravity so weak? And the three people who had that insight are these three folks, Savas Dimopoulos, Gia Diwali, and Nima Arkani Hamed. And I'm happy to show this picture because actually in a few weeks I will be going to his 60th birthday party. He is my academic father. He's my academic advisor. Okay? So they had this really great insight that if you just turn the question around, you arrived at a different set of possible answers. And those answers come down to thinking about fields again. So we've talked about fields, and I'd like to show you first an example of a field that you know and have seen, and probably you did this experiment when you were a child, or maybe more recently. You took a magnet and maybe spread some iron filings, and you saw this nice picture of how the iron filings line up along the field lines of the magnet. Okay? So here's a field, the magnetic field due to this magnet. And here is a picture representing those magnetic fields. Okay. So all forces can be represented in terms of field lines. Well, I don't know about all, but the forces we're going to talk about. Here is a simpler set, the field lines corresponding to the electrostatic force of a charged particle. Okay, here a positive particle on the left and a negative particle on the right. And these field lines just emanate in all directions from the charged particle. Okay? The same amount in every direction. Okay? And it turns out that gravity acts very much the same way. If I drew a picture of the Earth and its gravitational field lines, I would draw a picture of field lines either going in or going out. You actually kind of have a choice in gravity. And they would be going out the same amount in every direction. Okay? Now, it turns out that the force of gravity or of electromagnetism is proportional to the density of field lines. In other words, if I go to some place and I ask how many field lines are there in the little region of space that I'm in, say over here, the more field lines there are, the more force there is. Okay? And this leads us to the inverse square law of gravity and electromagnetism. Why? Because as you draw a sphere larger and larger, the area of the sphere grows as the square of its size, and so the density of the field lines falls off as the square of the size of the sphere. Okay? And the person who taught us this is this fellow, Sir Isaac Newton. He discovered that this 1 over r squared, this inverse square law of gravity, it works. Okay, it works for everything. It works for apples falling from trees. It works for the planets going around the sun, for the moon going around the Earth. And if you want to go celebrate this, you can walk into the quad of the university. You can see a little tree there, and that tree is actually a cutting of Newton's apple tree from which the apple supposedly fell and hit him on the head, or which he sat under and thought about this law of gravity. Okay, so what does that look like? It says that if we're at some distance from some source of gravity and we have some amount of force, and then we go out to, say, 3 times that distance, we'll have 1/9 the amount of force. Okay? Now, the idea that Arkani Hamed, Dimopoulos, and Diwali had was that we could make gravity weaker, which is what we want to do. We could explain why gravity is so weak if we could just make it fall off faster. Like, instead of the square of the distance, what if it fell off as the cube of the distance, or the 4th power, or the 5th, or 6th, or 7th? That would be great. Here's a picture of that, a graph of that. Instead of falling off like this red curve, how Newton tells us, where if I go out to 3 times the distance, I have 1/9 the force I started with. Let me just make it fall off as the 4th power, and then I'll have 1/81st. That would be great. So all we have to do, we can solve our problem, make gravity a lot weaker than electromagnetism if we just make gravity fall off, not as an inverse square law, but as a fourth power of the distance. There's a small problem, which is that Newton knew what he was talking about. Gravity really is an inverse square law. It really does fall off as the square of the distance. We've measured that. We've tested that over large ranges, ranging from, at the time in 1996, about 1 millimeter out to the distances of order the size of the solar system. So they said, well, sure, but what about on smaller scales? Maybe there are extra dimensions. So maybe there are extra dimensions. So this plane here you can think of as the ordinary dimensions that we are able to see. That direction, also that direction. I haven't been able to draw all 3 of them, so I'm just going to draw 2 of them. Here they are. And there are extra dimensions represented by these spheres. So at every single point in space, imagine that there was a little sphere. Okay? How little? Well, at the time, it could have been as much as 1 millimeter across. We now know that it's less than a micron across. That's still pretty big. I mean, kind of the diameter of your hair. Okay? If that was true, then gravity would fall off as an inverse square law at large distances, but at small distances, smaller than the size of the sphere, it would actually fall off as 1 over r to the 2 plus however many extra dimensions. So if it was a sphere there, one of those spheres, it would fall off as 1 over r to the 4th. If it was a 3-dimensional sphere, it would be 1 over r to the 5th. If it was a 6-dimensional sphere, it was 1 over r to the 8th. Okay? So, and here's a picture of what that would look like, kind of compressed. So here what I've done is I've compressed all of our ordinary dimensions to 1 dimension, this long one along this cylinder. And I've compressed the extra dimensions to 1, the one around the cylinder. Okay? And you see that here is a mass, and the field lines are going out. And if we stayed right near the mass, it would look just like we saw those field lines coming out of the charges or out of the Earth. But as we get farther away, the field lines notice that they have nowhere to go. They can't keep going. There's no more volume to spread out in, and so they get parallel to the ordinary dimensions, and they just go straight out in the ordinary dimensions. Now here I've drawn 1 of those, but there's really 3 of those. So what that means is on short distances, we get 1 over r to some big power, depending on how many extra dimensions there are. And on long distances, we get inverse square law. This is wonderful. We now have gravity doing exactly what we want. Except there's a little problem. We also measured electromagnetism, the electrostatic force, and it falls off as 1 over r squared, not just on scales bigger than a millimeter, but right inside the atom. Okay. And if the electrostatic force did the same thing, then it would stay in lockstep with gravity. It wouldn't end up any stronger than gravity. So you can't have it both ways, right? You can't have 1 over r squared electrostatics and long-range gravity and 1 over r to the 3rd, 4th, 5th, 6th, 7th, 8th short-range gravity so that gravity can be weak. Except that you can. And the way you do that has to do with those things that Cyrus mentioned, those branes. Okay, he talked about branes, which might be 2-dimensional or might be 3-dimensional. Let's imagine one that was a 3-dimensional brane, so a volume, like the universe we live in, and with things ending on it. Okay? And those things at the end were actually called particles, like quarks and leptons. Anyway, so what does that mean? It means that we're going to have the standard model particles. They're just going to be stuck to this measly 3-dimensional space. And gravity, it's going to be able to go out into the rest of the world and to all those dimensions into the bulk. And what that means is that while the standard model forces and particles are stuck on the brane, and electrostatics will fall off as 1 over r squared, gravity can dilute into the extra dimensions and get nice and weak. And so we can use this to reduce the value of the Planck mass. We can say that actually gravity intrinsically isn't that weak, it's just that it got diluted. And the bigger we make those extra dimensions, the more effective this works. And it turns out back in 1996, we could have brought the gravitational scale almost all the way down to this weak scale so that the ratio is about 3. Today we know that it's at least about 30. How do we know this? Well, we know this because we could if we have this lower Planck mass, that means all of a sudden quantum gravity can happen not by putting a gram of matter inside, almost a gram of matter inside a volume 10 to the minus 35 meters across, but by colliding particles at accelerators like the Large Hadron Collider and looking for quantum gravity, like the creation of a black hole. So we could smash protons together, make black holes, and of course those black holes would grow and grow and grow and swallow the universe, and we'd all be in trouble. Well, actually, fortunately not, because actually it turns out that black holes evaporate very quickly. If you made a black hole at the LHC, it would evaporate before it managed to cross the diameter of a nucleus. That's pretty fast. And in fact, one of the things I do is my students and I wrote a program to tell those big detectors that Cyrus described last week, ATLAS and CMS, what it would look like to even see a black hole. Because you wouldn't know it unless you thought about it carefully. So far, no black holes. And Cyrus says, there's no way we'll ever see black holes in an accelerator because string theory expects this Planck scale to actually be way up, 10 to the 19th times the proton mass. And what I'd say is that shouldn't stop the rest of us from looking. But what we agree is that the puzzles remain, and only experiment is likely to teach us how to solve them. So what we've tried to tell you is, why do we need anything beyond the standard model? How hard it is to build a theory beyond the standard model, but how beautiful and beguiling that theory can be, even if the mathematics are really very tough. And how we might, if we're lucky, be able to see into that world, but how so far it doesn't look like we're going to get lucky. But wait, over the next 2 years, we'll keep looking. And hopefully the LHC will produce some black holes, and we'll all be celebrating because it'll be the beginning of experimental string theory. Thank you.